What if I told you that right now, while you're reading this sentence, a machine built in 1977, older than the internet, older than cell phones, older than most of your parents' careers, is sitting in a region of space so cold, so dark, and so far away that sunlight itself takes more than a full day to crawl there? What if I told you that this machine is dying, slowly, on purpose, instrument by instrument, because the people who built it refused to let it go silent without a fight? And what if I told you that just weeks ago, NASA made a decision so quiet that almost nobody noticed it, but so significant that it changes everything we thought we knew about humanity's only working eyes and ears in interstellar space? This is not science fiction. This happened in April 2026. And the story behind it is stranger, more desperate, and more emotional than anything Hollywood could invent. Let's start with where this thing actually is. Voyager 1 is not in our solar system anymore. It hasn't been for over a decade. In August 2012, it punched through a boundary called the heliopause, the invisible wall where the sun's solar wind finally runs out of strength in the cold, dense plasma of interstellar space takes over. Think about that for a second. Voyager 1 left the protective bubble of our own star. It is now floating in the space between stars, in the literal void between our solar system and the next one. As of mid-2026, it sits more than 15 billion miles from Earth, over 25 billion kilometers. To put that in perspective, light itself, the fastest thing in the entire universe, now takes more than 23 hours just to reach it. And here's where it gets even stranger. By the time you finish reading this paragraph, Voyager 1 has already moved further away. It never stops. It is traveling at roughly 17 kilometers every single second, on a trajectory it locked in during its final planetary flyby of Saturn back in November 1980. Nothing is bringing it back. Nothing is slowing it down. It is gone, forever, deeper into the dark. But here's the twist that most people are not talking about. NASA expects Voyager 1 to cross an extraordinary milestone in November 2026, becoming the first human-made object in history to sit a full light day away from Earth. One light day. That means a radio command sent from California will take 24 hours just to arrive. And if the spacecraft responds, another 24 hours for that signal to crawl back. A full 48-hour round trip just to ask a machine a single question and get an answer. Read that again. This isn't a delay like a bad phone call. This is a conversation stretched across an entire planet's rotation twice over. And it's only going to get worse from here, because Voyager 1 is not stopping. Every single day the distance grows, and every single day the wait grows longer with it. Now, here's where the real tension of this story begins, because Voyager 1 isn't just far away. It's running out of power. Both Voyager spacecraft are powered by something called a radioisotope thermoelectric generator, essentially a nuclear battery that converts the heat from decaying plutonium-238 into usable electricity. It's brilliant engineering for its time, the only realistic way to keep a spacecraft alive for decades with no sunlight to rely on once it left the inner solar system. But plutonium decays, that's physics. That's unavoidable. And as it decays, the power output drops. Roughly 4 watts lost every single year, year after year, with no way to refuel, no way to repair, no way to send a maintenance crew across 25 billion kilometers of empty space. As of 2026, both Voyager spacecraft are producing less than half the electrical power they had when they launched. Think about what that means for a machine that has to stay warm enough to function in temperatures that would instantly destroy almost anything else humans have ever built. So what do you do when your only spacecraft in interstellar space is slowly starving to death and there's no way to feed it? You start making brutal choices. You start sacrificing pieces of the mission to save the whole. And that is exactly what happened on April 17th, 2026, when engineers at NASA's Jet Propulsion Laboratory in Southern California sent a command across that mind-bending distance to shut down one of Voyager 1's remaining science instruments, a device called the Low Energy Charged Particles Experiment, or LECP for short. This wasn't some minor backup sensor nobody cared about. This instrument had been running almost continuously since 1977, 49 years. It had survived flybys of Jupiter and Saturn, survived the crossing into interstellar space, survived decades of cosmic radiation. And now, on a quiet Friday in April, a team of engineers had to make the call to switch it off. Not because it broke, but because keeping it alive was costing the spacecraft a future. But here's where it gets worse. This decision didn't come out of nowhere. On February 27th, 2026, during a routine, carefully planned roll maneuver, the kind of operation Voyager has performed safely for decades, something unexpected happened. The spacecraft's power levels dropped suddenly and without warning. For a machine running on razor-thin energy margins, 15 billion miles from the nearest human being, that is the kind of moment that makes mission control's heart stop. Engineers realized that if the power kept falling, it could trigger something called the undervoltage fault protection system. Essentially, Voyager's own self-preservation instinct, kicking in automatically, shutting down components on its own without anyone choosing which ones. And that is the nightmare scenario, because once the spacecraft starts making its own emergency decisions, 23 hours away from any human input, there is no telling what gets shut off and what doesn't. The recovery process from a fault like that is lengthy, uncertain, and carries its own risks of permanent damage. So the team didn't wait. They moved first. They chose what to sacrifice before the spacecraft was forced to choose for them. This is not chaos. This is strategy. And it's strategy that was planned years in advance. Long before this crisis moment in February 2026, the Voyager science and engineering teams had already sat down together and quietly agreed on the exact order in which every instrument on both spacecraft would eventually be switched off, one by one, to conserve power while protecting the most scientifically valuable capabilities for as long as possible. Of the 10 identical sets of instruments each spacecraft originally carried into space in 1977, 7 have now been shut down on Voyager 1, 7 out of 10. The LECP was simply next in line on a list that engineers wrote years before they ever expected to need it. According to Voyager mission manager Kareem Badruddin at JPL, shutting down a working science instrument is never anybody's first choice, but with the alternatives being far worse, it was, in his words, the best option available. What most people are not seeing in this story is just how personal this loss actually is to the scientists involved. The LECP wasn't just collecting random data, it measured low-energy charged particles, ions, electrons, cosmic rays, streaming in from both our own solar system and from the wider galaxy beyond it. For nearly 5 decades, this single instrument helped scientists map the actual physical structure of interstellar space, something no other human-made device has ever been able to do, because no other human-made device has ever been out there long enough or far enough to try. It detected pressure waves rippling through the interstellar medium. It tracked changes in particle density in a region of the universe that, until Voyager arrived, existed only in theory and mathematical models. Matt Hill, the instrument's principal investigator at the Johns Hopkins Applied Physics Laboratory, wrote in an email that LECP was the instrument that helped scientists actually sense the moment Voyager crossed out of the solar system and into the space between the stars. Now it's gone dark, powered down, deliberately, to buy its own spacecraft a little more time to live. But here's where everything changes, because this isn't necessarily the end of the story for LECP. There's a backup plan, and it's bold enough that engineers have given it a name straight out of cosmology itself, the Big Bang. Not a metaphor for destruction this time, but for a complete and coordinated transformation. The plan involves swapping out a whole group of power-consuming components on the spacecraft all at once, replacing older, hungrier systems with newer, more efficient alternatives, all in a single, carefully timed operation. The goal is to free up enough electricity to keep the spacecraft warm, keep its remaining instruments alive, and potentially even bring the LECP back online. Think about the stakes of that decision. You only get one shot. There's no test run on the actual spacecraft itself because every single command costs nearly 2 days round trip, and any mistake, any miscalculation, could be the difference between extending the mission and ending it permanently. So how do you test something that risky when you're playing with the literal last surviving spacecraft of its kind in interstellar space? You don't risk your best asset first, you risk the other one. Voyager 2, slightly closer to Earth and holding slightly more spare power in reserve, has been chosen as the test subject. Engineers plan to attempt the Big Bang procedure on Voyager 2 first, during May and June of 2026, treating it almost like a guinea pig for an irreversible experiment on a 49-year-old machine that has already outlived every realistic expectation anyone ever had for it. If, and only if, that test succeeds, the team plans to attempt the exact same high-stakes maneuver on Voyager 1 no sooner than July 2026. And if that works too, there's a real documented possibility that the LECP instrument could be switched back on, resurrected from its forced silence, continuing to gather data on the structure of interstellar space that no human being and no other machine can collect from anywhere else in the universe. Let that sink in for a moment. 2 spacecraft, launched weeks apart in 1977, now separated by billions of kilometers, are about to undergo an experimental power transplant performed entirely through radio commands sent across light days of empty space, with engineers on Earth essentially operating blind, unable to watch what's happening in real time, unable to intervene if something goes wrong mid-procedure, simply sending the command and then waiting for nearly 2 full days to find out whether it worked or whether they just lost permanent contact with the most distant object humanity has ever built. And this is where the deeper, more unsettling layer of this story comes into focus, because Voyager 1 isn't simply old, it's becoming something almost unprecedented in the history of human exploration, a machine operating so far beyond the reach of real-time human control that it exists in something closer to its own independent timeline. Every command takes nearly a full day to arrive. Every confirmation takes nearly a full day to return. By November 2026, when Voyager 1 crosses that historic one light day threshold, mission engineers on Earth will essentially be talking to a version of the spacecraft that is, in a very real sense, already a day removed from the present moment they're living in. The Voyager they're commanding and the Voyager that exists right now, at this exact second, are not quite the same Voyager. There's a temporal gap baked permanently into the relationship between Earth and its furthest outpost, and that gap will only keep widening year after year, for as long as the spacecraft continues to function. What does the spacecraft actually have left after losing 7 of its 10 original instrument sets? 2 functioning science instruments remain active on Voyager 1, the plasma wave subsystem, which listens to the electromagnetic hum of the plasma surrounding the spacecraft, and a magnetometer, which measures the magnetic fields woven through interstellar space. That's it. That's what's left of a spacecraft that once photographed the swirling storms of Jupiter, discovered new moons hidden in its rings, captured the haunting, humbling image known as the pale blue dot, Earth reduced to a single, fragile pixel suspended in a sunbeam, a photograph Carl Sagan himself helped direct, and one that permanently reshaped how an entire generation thought about humanity's place in the universe. Voyager 2, slightly luckier in terms of power reserves, has managed to hang onto one additional instrument, the cosmic ray subsystem, which the team is hoping desperately to keep alive through the mission's 50th anniversary in 2027. 50 years. According to informed engineering projections, that anniversary is no longer a guarantee. It's a target the entire Voyager team is fighting to reach. 1 watt of power at a time, 1 instrument shut down at a time, 1 experimental Big Bang power swap at a time. The spacecraft were never designed to survive this long. Voyager's original mission, when it launched in 1977, was supposed to last about 5 years, just long enough to complete close flybys of Jupiter and Saturn. 5 years. That was the plan. Instead, in 1990, after both spacecraft proved they could keep functioning far beyond their original objectives, NASA extended the program under a new banner, the Voyager Interstellar mission, with an entirely new, almost audacious goal: reach the very edge of the sun's influence, and then keep going into the unknown space beyond it. Voyager 1 achieved that in 2012. Voyager 2 followed in 2018. And now in 2026, both spacecraft are still out there, still transmitting, still defying every reasonable expectation anyone ever had for a piece of 1970s technology. But the real story most people are not seeing is this. Every single watt of power lost on these spacecraft is permanent and irreversible. There's no solar panel to clean off. There's no battery to swap out by hand. There's no second source of energy waiting in reserve anywhere on either spacecraft. The radioisotope generators are decaying at a fixed, unstoppable rate dictated entirely by nuclear physics, and engineers cannot slow that decay down even if they wanted to. The only thing they can control is how the spacecraft spends the dwindling power it has left, and that means the entire remaining lifespan of humanity's only working interstellar probes now comes down to a series of increasingly difficult trade-offs, each one bringing the mission closer to an ending that is not a question of if, but only a question of when. And here's the part that should genuinely unsettle you. Once both Voyager spacecraft finally go silent, whenever that happens, whether it's this year, next year, or sometime in the early 2030s, there is currently no replacement mission anywhere close to matching what they do. No other spacecraft built by any nation on Earth has traveled far enough, fast enough, or long enough to reach interstellar space and keep functioning there. The next spacecraft humanity sends toward that boundary, whenever it eventually launches, will take decades just to reach the distance Voyager 1 has already traveled. For years, possibly decades, after the Voyagers finally fall silent, humanity may have no working presence at all in the region of space beyond our own solar system. The window we currently have, right now in 2026, listening to 2 fading machines whisper back data from the edge of the world we belong to, may not reopen again for an entire generation. Think about what that means for the scientists who have spent their entire careers working on this mission. Some of the engineers currently managing Voyager's slow, careful decline weren't even born when the spacecraft launched in 1977. They inherited a machine built by people who, in many cases, have already passed away, and now they are the ones responsible for deciding, instrument by instrument, watt by watt, what survives and what gets sacrificed. Every command. They said takes nearly 2 days to confirm. Every decision is effectively irreversible the moment it's transmitted, and every year the spacecraft they're caring for drifts a little further from Earth, a little further from human reach, a little further into a darkness that has never been mapped by anything human-made before it. So where does this leave us? As of mid-2026, Voyager 1 is still alive, still transmitting, still carrying humanity's voice and humanity's curiosity into a region of the cosmos that exists, for now, entirely outside our solar system's protective embrace. The test of the Big Bang power saving procedure on Voyager 2 is happening right now, in real time, even as this story is being told. The results of which will determine whether Voyager 1 attempts the same maneuver in July, whether the LECP instrument ever speaks again, and whether the mission stretches toward its 50th anniversary in 2027, or meets its end sooner than anyone wants to admit. Nobody, not the engineers at JPL, not the scientists who have devoted their careers to this mission, not NASA itself, actually knows how this ends. There is no guaranteed outcome here. There is only a slow, careful, deeply human attempt to keep a 49-year-old machine breathing for just a little longer, watt by precious watt, against odds that grow heavier with every passing year. And maybe that's the real story buried underneath all the technical details and mission updates, not just what Voyager detected at the edge of the solar system, but what it continues to detect, right now, in real time, from a place no human being has ever been and may never go. A region of space where sunlight is nothing but a distant memory, where temperatures plunge to levels that would shatter most materials humans have ever engineered, and where a single aging spacecraft, built before most of its current caretakers were even born, continues quietly reporting back, one fading signal at a time, on what actually exists in the silence beyond our sun's reach. How much longer can it last? Nobody knows. What will the Big Bang procedure reveal when engineers finally get the results back from Voyager 2 this summer? Nobody knows. And when the day finally comes that Voyager 1 sends its last signal across 25 billion kilometers of empty space, and that signal simply never arrives, will we even immediately understand that the silence means it's over, or will we spend another 23 hours waiting, hoping for an answer that is never going to come?